Everybody, bienvenue à tout le monde. Bienvenue à todos. Hello everybody. So we are happy to hear the PhD defense of Iván Rasskin, a polytopal approach to Apollonian packings and discrete knotted structures. Before starting, let me introduce the members of the jury. So let me start with Miss Catherine Stench in the University of Boulder, Colorado, and Mr. Hao Chen from Göttingen, University of Göttingen. Here to my left, Éric Collin de Verdière from the CNRS, Centre National de la Recherche Scientifique, in Université Gustave Eiffel in Paris. The thesis director, Jorge Ramirez Alfonsin, Université de Montpellier, and myself from Université du Littoral Côte d'Opale in northern France. So it's yours. You have about 45-50 minutes. Please go.
First of all, I want to thank the members of the jury for having accepted to be here today. So let's start. I'm going to present my work on PhD, a polytopal approach to Apollonian packings and discrete knotted structure under the supervision of Professor Jorge Ramirez of the University of Montpellier. So in this work, we relate three family of objects. Polytops, they are a combinatorial family of objects. Apollonian packings, which are a geometric objects, and knots, which are more topological objects. So let's start by introducing what is Apollonian packing. Apollonian packing starts with the problem of Apollonius, a very old problem from 2,300 years ago. It's how many circles are tangent to three given circles like that. So it's a problem apparently raised by Apollonius of Perga. So we have three circles like that, and we want to add a circle which is tangent to the three. How many solutions we have? In a general case, we can have up to 8 solutions, but in this specific case, we only have 2 solutions that are by describing a circle in each curvilinear triangle. Now, if we start with a configuration of 4 circles, and we add in each curvilinear triangle a circle like in the Apollonian way, we obtain new curvilinear triangles. So we can continue to add new circles. We continue to the infinity to obtain at the end an Apollonian packing. Apollonian packing has many applications in chemistry, physics, and mathematics. For example, for the study of foam structures, also for fluid emulsions, hyperbolic geometry, also in geometric group theory, and numbers theory. And this is the aspect that we are interested in this thesis, the applications of Apollonian packings in number theory. And also we are going to apply Apollonian packings into a novel direction of mathematics, which is knot theory. So in this talk, there are 2 parts, the applications of Apollonian packings in number theory and also the Apollonian packings and knots. So first of all, what are the relations between Apollonian packings and number theory? This relation starts with the Descartes theorem. So Descartes and the Princess Elizabeth of Bohemia, they were working on the problem of Apollonius, and they were able to find an algebraic relation which is equivalent to this quadratic equation. So the curvatures, which are the inverse of the radii of 4 power tangent circles, must satisfy this quadratic relation. Almost 300 years later, Frederick Soddy used the Descartes theorem. He noticed that if the 3 curvatures are integers, satisfying that this quantity here is also an integer, then the curvatures in the corresponding Apollonian packing will be all integers. We call this Apollonian packing an integral Apollonian packing. There are some generalizations of Apollonian packing, for example, in high dimension. we can, instead of working with 4 pairwise tangent circles, we can start with 5 pairwise tangent spheres. In that case, Sodi found an analog of the Descartes theorem in dimension 3, and then Gosset found an analog of the Descartes theorem in every dimension. So we can have an analog of the Descartes theorem in every dimension. And so they use this Descartes theorem to find an integrality condition that he used to construct integral Apollonian packings in dimension 3. A different kind of generalization can be done by, instead of changing the dimension, we can change the initial set. So instead of working with a tetrahedral packing, we can, for example, change the initial set to an octahedral packing. Why we call it octahedral? Because the combinatorics, the tangency relation, can be coded in the first case by a tetrahedron, in the second case by an octahedron. In that case, Gettel and Malus found a quadratic relation which is equivalent to the Descartes theorem for octahedral packings. And they use it to construct integral Apollonian packings with the combinatorics of the octahedron. So there are so many questions that we can ask in number theory. In this thesis, we want to answer this question. Is there a more general Descartes theorem which applies the other generalizations? Can we find integral Apollonian packings with other combinatorics? Is there any relation between the numbers of an integral Apollonian packing with different combinatorics? Can we say something about the numbers of an tetrahedral packing in relation with an octahedral packing, for example? So to answer this question, we're going to use polytops. What is a polytop? A D polytop, or a polytop in dimension D, is the convex hull of many points in Rd. So just in dimension 2 is a convex polygon. So dimension D is the generalization of a convex polygon. In dimension 3 is a convex polyhedron. In dimension 4 we cannot draw it because we are in dimension 4, but we can project it. For example, here in dimension 3 we project it into a planar diagram, which we can study the combinatorics. In dimension 4 we can project it into a 3-dimensional projection. For example, this is the projection of a hypercube, which is the analog of the cube in dimension 4. A natural family of polytops are the regular polytops, which is just the generalization of regular polygons. In dimension 2, there are infinite many cases of regular polygons. For example, triangle, the regular square, regular pentagon, and we can continue to infinity. But in dimension 3, there are only 5 regular 3 polytops, which are the famous Platonic solids. In dimension 4, we have 6 regular polytops, the 4 simplex, which is the analog of the tetrahedron, the octuplex, which is the analog of the octahedron, the hypercube, which is the analog of the cube, the 24-cell, which is the analog of a cambicina, the analog of a rhombohedron, which is not regular in dimension 3, 600 cell, which is the analog of the icosahedron, 120 cell, which is the analog of the dodecahedron in dimension 4. In dimension 5 and above, there is only 3 regular polytops, the analog of the tetrahedron, octahedron, and cube. So this is the complete list of regular polytops in every dimension. How to construct packings from polytop? Well, this is previously studied by many other mathematicians, and in this thesis we try to synthesize these works and give some closer definition. So the recipe, it starts from a polytop like that, satisfying that all the vertices lie outside the sphere. So now from each vertex, we're going to put a light, let's say a gray light, and we are going to illuminate the sphere. And for each vertex, we have illuminated areas, which are, in this case, the spherical disk. Then we can project it with the stereographic projection, and we have an arrangement of disk. We start from a 3 polytop, and we have an arrangement of disk in dimension 2. So this connection can be done in every dimension. This 3 step, we have called it the ball arrangement projection. So there are 2 interesting cases. The first case was when an edge, if we look at that one edge, if the edge is cutting the sphere transversely, then the vertices, which correspond to 2 disks, these are disjoint. If the edge is cutting transversally, the areas are disjoint. But if the edge is avoiding the sphere, the illuminated areas will be intersected. So in the middle case, when the edge is tangent to the sphere, the illuminated areas will be tangent. if the polytope satisfies that every edge is tangent to the sphere, then we say that the polytope is edge-scribe. And this is the case that we are interested in. We will say that a packing is polytopal if it comes from an edge-scribe polytope in dimension p+1. We allow also to apply, after the polar region projection, a Mobius transformation. So at the end, we obtain again a packing, and we can change by a Mobius transformation, and all of these cases will be polytopal in our definition. So why we allow to apply a Mobius transformation? Because the properties that we're interested in are preserved under Mobius transformation. So this is a natural question. We have two different realizations of the same combinatorial polytope, both edge-scribe, which gives different packings. Are these packings connected by a Mobius transformation? If this is the case for every edge-scribe realization, we say that the polytope is Mobius unique. In that case, if the polar incorporation of all edge-scribe realizations are connected by Mobius transformation. In this case, we know that this is the case. In dimension 3, it works because of a consequence of the mid-sphere theorem of Reichswald and Scheinerman that says that every polytope in dimension 3 are edge-scribable and Mobius unique. So this Mobius transformation always exists in dimension 3. So for example, if we wonder for the Mobius uniqueness of regular polytopes in dimension 3, so the mid-sphere theorem will work. So for regular and irregular polytopes, they are all Mobius unique. For example, in dimension 2, we can find two polytopes which are not Mobius unique. It is easy to prove that the only Mobius unique two polytope is the triangle. So in this thesis, we have proved that almost all the regular polytopes in other dimension are Mobius unique, except for the 600 cell and 120 cell one that we don't know. But we conjecture that above dimension 2, all edge-scribable polytopes are Mobius unique. Some properties of polytopal packings that we are going to use for construct Apollonian packings. The first question is that the tangency graph is given by the skeleton of the polytope. So if we want to know the tangency relation, we must look at the polytope, the skeleton of the polytope. The second property is that the duality of the polytope translate into dual configuration here, which will be the duality will be translated into orthogonality. And then we can use each dual sphere to construct an analog of the Apollonian group, which is the group generated by the inversion on each dual sphere. Then if we apply the inversion on each dual sphere to the initial set, we obtain new copies of the initial set by preserving the tangencies. So if we continue to apply this group, the union of the orbits give us a polytopal Apollonian packing with the combinatories of the initial polytope. The polytopal Apollonian packing, by definition, is the union of all of the orbits of the action of the Apollonian group acting on the initial set, the polytopal packing. So to answer the first question, is there a more general Descartes theorem? We use this connection, polytopes and packings, to give our own generalization of the Descartes theorem that we have called the polytopal Descartes theorem. Before giving this, we need two definitions. The first definition is the mid-sphere ratio, which is defined for every regular polytope, which is the ratio between the half of the edge length divided by the radius of the sphere tangent to every edge. For example, for the triangle, the mid-sphere ratio is square root of 3. For the tetrahedron, the mid-sphere ratio is the square root of 2. The second definition is the polytopal curvatures for every polytopal packing. So, for example, here we have a polytope behind. For every face of the polytope, we're going to define the polytopal curvature of the packing with respect to this face as the arithmetic mean of the curvatures corresponding to the vertices of the face. For example, here the face 1, 2, given by 1, 2, 3. The polytopal curvature with respect to this face is the arithmetic mean of this 1, 2, and 3. So with these two definitions, by using Lorentz geometry, we prove that the polytopal, for every polytopal packing coming from a regular polytope in every dimension, and for every flag of this polytope, A flag is just a sequence of faces which are increasing in the dimension and they are included one into the other. So we start from a vertex, then an edge, then a two face, and we continue to the polytope. Then the polytopal curvatures of these faces must satisfy this quadratic relation. The coefficients in this quadratic relation are the mixture ratio of the faces in this flag. For example, if we apply to the tetrahedral case, we start from a flag, for example, the flag given by the vertex 1, the edge 1, 2, the face 1, 2, 3, and the polytope 1, 2, 3, 4. Then we have that the polytopal curvature of the elements in this flag must satisfy this quadratic relation, where the numbers 3, 6, and 2 are given by the mixture ratio of the triangle and the mixture ratio of the tetrahedron that we said that were square root of 3 and square root of 2 would give us 3, 6, and 2 here. And now we replace by the definition of polytopal curvature, we replace by the arithmetic mean, we have a more complex relation that we can simplify and obtain the classic Descartes theorem. So the polytopal Descartes theorem applies the classic Descartes theorem. Not only that, but the polytopal Descartes theorem applies many other generalizations, like the tetrahedral case, like the orthoplicial case, like the simplicial case, and every dimension. Not only that, but we can use this polytopal Descartes theorem to obtain new integrality conditions to construct integral Apollonian packages with different combinatorics. We can obtain, for example, other integral Apollonian packages which have been also discovered, for example, by Soddy, the classic case, Getteler Malus for the tetrahedral case, the cubical case given by Stench, the bold Bachelor and Havland, which give us the icosahedron. We found new integrality condition to construct integral Apollonian packages with the combinatorics of the icosahedron. Just to notice, the first three cases, the curvatures are real integers. In the second case, the curvatures are a linear combination of integers and phi, if phi is the golden ratio. So, for the last question, let us give an example. We wonder, for example, if we start from a polytopal packing coming from a polytope, for example, the cube, and we have another polytopal packing, for example, in another dimension, in dimension 3, and with a polytope given, for example, for the orthoplex. We wonder if the numbers here are contained in the numbers here. So if we look closely, we can see that the numbers within finite iteration, we can find the same numbers, but what about the infinite case? How can we prove that all the numbers are included? So for answer this question, we have introduced a new tool that we have called Apollonian section. This Apollonian section has been inspired by the geometric operation of cutting with a plane. So for example, we know if we start with a octahedron, we intersect with a plane, we obtain, for example, a square. This square here, so a two-polytope. In the same way, if we intersect the orthoplex with a hyperplane, we can obtain, for example, an octahedron. So is the same case for the corresponding packings? Can we intersect the orthoplexal packing with, for example, a plane or a sphere and obtain an octahedral packing? In this configuration, it's not very clear, but maybe we can change the projection. So if we look at this configuration on the sphere, we have this arrangement of spherical disks. So the three little disks correspond to the disk behind. Then we can change the projection. One disk of, for example, this disk here comes to the middle, to the North Pole, becomes the outer disk. The four disks surrounding are these four disks, and the disk in the South Pole is the little disk. So we can do the same for the orthoplex, which is the analog with the octahedron in dimension 4, and we obtain this configuration. And now it's clear that in this configuration, in this projection, we can find an octahedral packing inside an octahedral packing just by intersecting with a plane. What about the Apollonian packing, the corresponding Apollonian packing? We start to fill in the space in the Apollonian way. Can we say that this configuration can be found here by intersecting with a plane? So at the first iteration, we cannot found it. So we start with some colors, we start doing iterations, and after a few iterations, we can obtain in this orthoplexal packing the same configuration as the octahedral packing. So how can we prove it? that this is the case for infinite iterations. So we're going to use Apollonian section. What is an Apollonian section? So we start from Apollonian packing, which is just the Apollonian group acting on the polytopal packing, which gives us the polytopal Apollonian packing. And we want to understand substructs which are inside. So instead of taking the whole group, we're going to take a subgroup. Instead of taking the whole set, we're going to take a subset. So which gives us a subset of the Apollonian packing, but with keeping information of the action group. For example, the Apollonian packing is trivially the definition of Apollonian section. But we have also interesting cases, for example, orbits. The orbits is the Apollonian packing acting on one element. Give us just the orbit on one single element. We have also parabolic sections, which are interesting. We take a parabolic subgroup of the Apollonian group, we act on the whole initial set, and give us a substruct of the polytopal packing, which can be interesting. We introduce this definition. We are going to compare two different Apollonian sections, and we are going to say that they are algebraically equivalent if there is an equivariant ejection between them. With this new tool, we have proved that every orthoplesial packing contains an octahedral packing, but also a tetrahedral and a cubical Apollonian section. We're going to illustrate for the cubical case. So we start from this orthoplesial packing. We are going to maybe put it like that in a crossed way. So we want to find cubical structures here. So we are going to consider the dual packing, which gives us the orthoplesial Apollonian group generated by 16 spheres which correspond to the vertices of the hypercube. And here we have too many spheres, so we're not going to take less spheres. We're going to take a parabolic subgroup generated by only 6 spheres, 6 blue spheres. These 6 blue spheres has been chosen to be orthogonal to this plane, which cuts the initial set by 2. So we take these 6 spheres, which are orthogonal to this plane, and we apply to the initial set. So these 6 spheres and the initial set, we can construct a bijection to the cubical case and its dual. And then this bijection gives us an equivalent bijection between the packing obtained here, which is the action of the group generated by the blue spheres on the initial set. So this packing here is algebraically equivalent to this cubical packing. So we say that this is a cubical Apollonian section. Not only that, but if we cut by the same plane as before, the middle plane, then we can obtain some information. For example, if we color with, let's say, black, the spheres at one side of the plane, and with white, the spheres at the other side with white, and we color here, then we obtain a proper coloring of the cubical packing. So here, there is no 2 black discs, for example, but they are tangent. So here, the spheres that are above this plane and correspond to black disc here. The spheres which are below are the white disc. So this structure will be interesting for the next section to construct knots. Then we use this Apollonian section, the last result, to answer the question about the relation between numbers. We prove that every integral, tetrahedral, octahedral, or cubical Apollonian packing can be obtained as an Apollonian section of an integral orthoplesial Apollonian packing. So if we start from the first question, now we have a method to start from, for example, an integral cubical Apollonian packing, and then we can find an integral orthoplesial packing with many spheres, which inside there is an Apollonian section, which is equivalent, and the curvatures here are exactly the same as here. So all the numbers here can be found in this initial set. Just to notice that the combinatorics are different. For example, these 2 discs, the disc with curvature 20 and 29, correspond to these 2 spheres, which here are tangent and here are disjoint. So with this last question, we finish this part of Apollonian packings and number theory. And now we start the second part of this talk, which is Apollonian packings and knots. So regarding knots, we wonder about a specific construction related with knots, which are the necklace representation of knot and links. So a necklace representation of a knot or a link is just a sequence of tangent sphere, which the tangency graph is isotopically equivalent to the given knot. For example, here we have the trefoil knot. Here we have a necklace representation of the trefoil knot. This kind of construction has been very useful in molecular biology, for example, for modelizing polymers. And also, we can find this kind of configuration in hyperbolic geometry for studying the three manifolds with low cast volume. So the natural question about this kind of representation is what is the minimum number of spheres needed to construct a necklace representation? So answering this question is the same to compute the Bode number. So the Bode number of a knot or link is exactly the minimum number of spheres that we need to construct a necklace representation of this link. So an example, a trivial example, the Bode number of the trivial knot is just 3, so we need only 3 spheres. Mayara, who introduced the Bode number, he proved that the Bode number of the simplest non-trivial link, the off link, is exactly 8. So he gave an optimal construction, and he proved that with 7 spheres, it's not possible to make a half link. Then he proved also that the Bode number of the trefoil knot must be between 9 and 12. So he gave an optimal construction. He proved that we cannot do it with 8 spheres. So nowadays, we don't know what is exactly the Bode number of the trefoil knot or any other knot. But for example, Mayara conjectured that the Bode number is exactly 12. So what about the Bode number of other knots? So actually we don't know, but in this thesis we have done the first general linear upper bound of the Bode number in terms of the crossing number. So we have done a constructing proof, which starts from a diagram like that, for example, like crossings. And the algorithm gives us a sphere packing with 5 times the number of crossings. And inside this sphere packing, inside the tangency graph, we can find a Hamiltonian path, which is isotopically equivalent to the given knot or link. But we conjectured, however, that this construction is not optimal. I conjecture that for every alternating link, so every link which alternates between upper pass and underpass, the Bode number must be 4 times the crossing number. So why we conjecture this? Because we have found some optimal construction by using the Toplissial Apollonian packing. So we have the first case that we look at was the Mayara's optimal construction for the half link. We noticed that this optimal construction is actually the Toplissial packing. So we want to look, maybe there are some other knots. For example, we know that there is not the trefoil knot, trivially, because here we have 8 spheres, and the Bode number of the trefoil is 9. We know that is greater than 9. But maybe if we apply the Apollonian group, we fill the space in an Apollonian way, maybe here we can find a necklace representation of the trefoil, and actually we can find it after one iteration. An interesting thing is that we count the numbers of spheres, we can find a conjecture optimal construction with only 12 spheres. What about other knots? Maybe, for example, the next knot, the knot for 1. Can be found here in this Toplissial Apollonian packing? Well, the answer is yes. We have proofs in this thesis that every link can be constructed in any Toplissial Apollonian packing. So to do this, we use the Alexander's theorem. We start from a link. For example, here the trefoil link. The Alexander's theorem says that every link can be put it like that as a closed braid. And then this closed braid, we're going to draw it inside a square grid diagram. So the crossings are going to be inside each square, and then the closure are going to be edges of this square grid. On the other hand, we're going to start from orthogonal packing, an arbitrary orthogonal packing, and then we are going to apply a Mobius transformation, which is given by the inversion of a contact point of 2 spheres. And we obtain this configuration where these 2 spheres becomes 2 half space, and the other spheres become this configuration of 6 spheres we have 4, and inside we have 2 little spheres, which are inside. We know that this is always the case because of the Mobius uniqueness of the octuplets that we have proved in the first part. Then we're going to apply the Apollonian packing. So we start from initial set, we consider the dual packing, we apply the inversions, and we obtain a huge number of spheres. So we don't need this huge number of spheres. We're going to, instead of taking the Apollonian packing, we're going to take an Apollonian section, only with 4 elements of the Apollonian group, which give us a subgroup, a subset of the other construction. But in this subset, it's enough to find a square grid. In this square grid, we can easily embed the construction given by the square grid diagram. For the crossing, we're going to use the 2 little spheres. So this can be done for every node. Then we come back with the inverse of the Mobius transformation, and we obtain the necklace representation inside the orthogonal packing, the Apollonian orthogonal packing. Because this can be done for every link can be formed in the orthogonal Apollonian packing. This construction is interesting because it gives us, for example, for a family of nodes, the 2 break nodes which are given by the closure of only 2 break, we can obtain a conjecture optimal construction. But for other nodes, for example, the node 4 one that we want to construct in an optimal way, this construction fails because here we have more than 2 breaks, and for closing the breaks, we need more spheres than 4 times the crossing number. So to construct optimally this type of nodes, we're going to use another property of these nodes, that these nodes are rational links. So what is a rational link? We start from an arbitrary link, like that, and we're going to consider a transversal sphere, it's called the factorizing sphere, which cuts the link in a transversal way, and we consider just the intersection. In this intersection, we have closed arcs like this one, and we have also open arcs, which the endpoints of these open arcs are in the boundary of the sphere. And then we can define some operation of tangles. For example, there is this operation, the flip operation, which do the reflection on this plane, and give us a new tangle. So we can apply the half twist operation that takes these endpoints and add a crossing. We can do this in 2 different ways, a positive way and a negative way. Then we squish, and because we are in topology, we can do that without changing the topology. And that gives us a new tangle. With these 2 operations, Conway defined an algorithm. It's called the Conway's algorithm, which starts from a trivial tangle like that, and iterates, flips a half twist, and the number of half twists that we're going to apply is coded in a sequence of integers. For example, if we start from the trivial tangle like that, given by the sequence 2 minus 2 minus 3, we start from this trivial tangle, we apply the flip, then we add 3 negative half twists, and we apply a flip, then 2 negative half twists, then we apply a flip, then 2 positive half twists. At the end, we obtain a rational tangle. So this kind of tangles, so this method that it can be, this is very simple, but can give us some complex X structure, has been very useful to study topology of the DNA. So proteins that it can be the topology of the proteins in the DNA. What we call rational is tangles, because instead of working with tangles, we can work with rational numbers. So fraction can be also infinity, so Q can be 0. And then the flip operation corresponds to take the inverse, so we exchange the numerator and denominator. And the half twist operation, the positive and negative half twist, correspond to adding plus or minus 1. So we have again a Conway's algorithm defined by the same operation, but in this case the trivial tangle is infinity. If we apply for the same sequence as before, we start from the infinity, then we flip the infinity, we obtain 0, then we add 3 negative twists, so we add minus 3, then we flip, then we add minus 2, then we flip, then we add plus 2. And at the end, we obtain a continuous fraction, which is given by this sequence of integers. This continuous fraction gives us a fraction, 11/7, At Co, we prove that is in bijection with all the classes of this tangle obtained by the same sequence, all the class of all the tangles which are isotopically equivalent to this tangle. So this class of tangles can be named by tangle 11/7. So this is the connection between rational numbers and rational links, the rational tangles. So a rational link is just the closure of a rational tangle. So now we're going to construct rational links by using Apollonian patterns. In particular, we're going to use the cubical Apollonian section that we have introduced before. So we have here cubical Apollonian section of the orthogonal packing, which corresponds to a cubical packing. How we're going to construct rational links? So we start from factorizing the tetrahedron instead of factorizing the sphere, which is the discrete version. We look at only the sphere which are inside this tetrahedron. So here we have the spheres inside this tetrahedron. And inside these spheres, we're going to consider paths of consecutive tangent spheres, which start at one vertex of the tetrahedron and ends in another vertex. So here we need only two paths. And that gives us an orthocubical tangle, a discrete version of tangles in this package. Then we have the flip operation, which is given by the reflection on this plane. So we reflect here. And we have also the half twist, which we do in spherical inversions. We push this structure here, and we can add a positive half twist, and we can add also a negative half twist. Then we have the two operations, and we can define an analog of the convex algorithm for this kind of package. So we start from the same algorithm with these two operations, and we start from this initial configuration where the trivial tangle is given by these two paths. For example, if we apply for this sequence, the sequence given by 2 and 2, we start with one flip, we obtain this construction, then we add a half twist. So the previous tangle comes here. We add a half twist, so that gives us a new tangle. Then we apply a half twist. So the previous construction comes here. We obtain a new tangle. Then we apply a flip. And we apply again a half twist, give us a new tangle. And we finally apply the last half twist and give us the tangle, the rational tangle given by the fraction 5/2. So there is a very interesting thing of this construction. If we consider this construction, the middle plane, which cuts the construction by 2, we project it on this plane, we obtain the cubical packing, the path comes here, and in this construction, there is the information about the fraction of the tangle. So to do this, we are going to consider the last, or the first edge of this construction. So this first edge connects this sphere and this white sphere, the little one. We are going to consider the contact point, which is this free point. We have called it the first point of the tangle, and we have proved that the inversive coordinates of this point contains the information of the fraction. We can use this result to prove that this point is the intersection of this quarter of circle with the line with the slope, the square of the inverse of the fraction. So this can be seen as a geometric proof between the correspondence of tangles, which are topological objects, and rational numbers. If we come back to the 3D, we have our necklace representation of the tangle, and then we can use the edges of the tetrahedron before we close, and we obtain a necklace representation of the knot that we wanted to do, the rational knot for 1. If we wonder if this is an optimal construction, actually not, because we count the sphere to have more than 4 times the crossing number. But actually, at the first step of the algorithm, there is an simplification that we can do, that we can always do. We can, instead of starting from a trivial tangle, we can start with a tangle with a one crossing, and the first four spheres can be saved, which give us a conjectured optimal construction of this knot. So this can be done for every rational knot or link, which gives us the last result of this thesis, that for every rational link, the Paul number is bounded from above by 4 times the crossing number. With this part, we close the loop. Thanks for that.
Thank you very much, Ivan. Now is the time for questions. We will start with Professor Stench. Do you hear us?
Yes.
Yes.
So I have a quick question. Do we rotate through several times with different questions? Like, should I ask all my questions at once, or should I just ask one question at a time?
Sorry, I didn't get it. Can you repeat, please? Oh, as you wish. You can ask your questions all in one shot. I mean, one after the other. Yeah.
Okay.
Do as you wish.
How long does the question period last?
You are free to take as long as you need.
All right. So a first question that I have is about the polytopal Descartes theorem. And I was just wondering, what's the inspiration behind the idea of generalizing this notion of curvature just from vertices to edges and faces?
Yes, so the inspiration was that every regular polytop, there is a fundamental chamber, which is taken by a vertex, then the half of the edge, then the half of the face, and we have like a fundamental simplex. This fundamental simplex, this is the simplex that we want to obtain in the polytopal Descartes theorem. So every vertex of this fundamental simplex, if we translate like the curvature of these vertices, we have to consider the generalization of curvatures on each face. I don't know if it was very clear. So, for example, in every regular polytop, we have this fundamental simplex that every vertex corresponds to the barycentric of a face, and that gives us the arithmetic mean of a curvature.
So does that give an interpretation of these other kinds of curvatures in terms of the Apollonian packing? Like the curvature of a vertex becomes, be the curvature of the circle in the Apollonian packing.
Sorry, I didn't understand that.
So the curvature of associated to a vertex becomes the actual curvature, 1 over the radius of the circle in the packing.
Yes. Yes.
So what is the curvature of an edge in the packing?
So if we look at the polytop, we have the edge, and we can consider the barycenter of this edge. The barycenter is given by taking the arithmetic mean of the coordinates of the vertices.
Mm-hmm.
So now we look the curvature as a linear product, as an inner product in the Lorentz space. We're going to translate this relation of barycenter, which is the arithmetic mean of vectors, with the curvature. So now the curvature of an edge will be the arithmetic mean of the corresponding curvatures of each vertex.
I see. Okay. So so another question that I had relates to the continued fractions that you were just talking about at the end. And so I find this interpretation very interesting. So normally I think of continued fractions as being a process of Mobius transformations for the upper half plane. And so you think of the continued fraction for some rational point as an orbit, some word in the action of Mobius transformations just on the upper half plane. And the action of SL2Z. And so what I'm wondering is whether this interpretation is essentially the same as that geometric interpretation under some sort of equivariant relationship. If there's some way to relate the two interpretations.
Yeah, that's an interesting question. Yeah, I think it probably would be the same. So at the end, we are looking at rational points in the circle. So.
Yeah.
Okay.
But you haven't written down a way of relating the two?
I don't know.
Yeah. Okay. Just curious. Okay. Well, that's enough questions for now, and then because I want to let everybody have a chance to go around with questions, and then maybe I'll have some more questions after.
Sure. Thank you. So we switch to Professor Chen, please.
Hi. So I have a question about this conjecture that every H-squared polytope is Möbius unique.
Yes.
So how confident are you about this conjecture?
I think it would be true, but I don't know how to prove it. Maybe there's a result in hyperbolic geometry, which says that if you fix the hydral angles, maybe the polytope is fixed under isometries.
Okay, so me neither. I don't know if this is true or not. So, but do you know a thing about the universality of polytopes?
Oh, sorry?
Universality of polytopes.
No, I didn't say it about the.
So yeah, so I just so I don't know if the conjecture is true, but a remark is that in higher dimensions the polytopes can be as crazy as possible, and I really doubt that so something that nice could happen. But if that really happens, that would be a big news, and I would be very happy. So it's just a remark like that.
Yeah.
But do you have any like insight that would make you believe that this is true?
I feel like there is some rigidness of hyperbolic rigidness that would be maybe the correct tool to apply, but I don't.
So you think so you think there is kind of rigidity there?
Yes.
Okay. Thanks. Yes, that would be all my questions. Thanks.
Thank you. So now we switch to Professor Conan de Verdière.
Yes, thank you very much. For a nice presentation. So let me start. So since I'm in computer science, I have a few questions. Well, one question about the tools you use to prepare your slides and also the figures.
Okay.
You mentioned in the thesis that it's called polytopal, and I'm wondering how quickly it runs, what it relies on.
Yeah.
Do you rely on circle packing algorithm, or do you? And so, can you say a few words about that?
Yes. Well, this polytopac is used Lorentz geometry. So at the end, we code every sphere as a vector, and Mobius transformation is just matrix applying of these vectors. For example, for construct the nectar representation, we use the circle packing algorithm. And then we use the package of Mathematica to give the colors and the plot.
So am I right in assuming that all computations are exact, except perhaps those which rely on the circle packing algorithm?
Yes, that's it. Because if we use coordinates algebraic, Mathematica allows to use algebraic numbers. So, for example, for the orthocubical representation, we can work with 1 plus √2, and these are always algebraic values. But for example, for the circle packing algorithm, it's always approximative values. We can, I think there is also a rigidity side that we can expect that a number after a few iterations, we can define which algebraic number is because of the Mostow rigidity theorem.
Thank you. Another question, which is a very naive one. So you didn't talk much about Lorentzian geometry in your slides,
No.
but in the thesis it uses Lorentzian geometry a lot. So my question is very naive again: is Lorentzian geometry crucial to develop your tools and your proofs, or is it just a convenient way of phrasing things?
No, it's for using the proof to go into the demonstration. We need the algebra, linear algebra, and we need the Lorentzian geometry. So it is the good frame to prove that the two spheres are always disjoint under Mobius transformation. It's a very simple tool, actually. So that's because we are in higher dimension. It's maybe sometimes it's not so clear to see what is happening.
I see. Thank you. Another question. So you, in your construction, when you start with a set of points outside the unisphere in your project, you consider the illuminated region.
Yes.
This is reminiscent, at least to me, of constructions on the Delaunay triangulation and Voronoi diagrams,
Yes.
where you have set of points in the plane and you lift them, but typically you lift them on the paraboloid or the parabola.
Yeah.
Is there a connection, or is it just?
I don't know. It's just a question. Maybe. Yeah, there are some works on polytopal quadrics and parabolization, but yeah, I should think more.
Okay, yeah, I don't know the answer either. Thank you. Another question. So it's more. I'm switching to the to the second part of your talk. You're considering links and nodes and links, and you want to represent them as a contact graph of spheres.
Yes.
But in general, it could be also interesting to do this with graphs. So consider a graph which is embedded in R3, yes, and you would like to represent them using also contact necklace representations, as if you wish, up to ambient. You want to preserve the ambient isotopy class. Would your technique work as well for such graphs instead of links?
For planar graphs, yes, because we can use it for circle packing algorithm.
Yeah, but the graphs are not planar in general.
But no planar graphs depends, but there is no depends on the family. It was the first part of the thesis that we were comparing linkless graphs with sphere packer with graphs. I'm trying to do some comparison, but actually there is not there is not a good generalization of planar graph that works for circle packing or 3D. What are the graphs that we can do with the spheres? This is another question.
No, but okay, maybe I was not clear. But so instead of having a link in R3,
yes,
you consider now almost a link, except that you have a few vertices where several you have several edges that can lead from there, and you want to represent them. So typically, the vertices would be special spheres.
Okay. Yeah. Maybe this construction actually we take only some edges, but there are more edges in this construction than sigma. We can think about a target graph, or maybe we can approximate with this kind of algorithm. But yeah, this is a good perspective. Yeah. At the end of the work, we try to do some other construction instead of not. We try to do surface. For example, we were able to do some construction by using bases of this orthophysical complex. To construct the surface of a leaf, this kind of manipulation. But yeah, this is a good question. We don't know for graph, spatial graphs. I think there's some work to do.
Okay. I have a last question, if I may. So what I find okay, all this is about representing links as geometric objects like touching spheres. You have also the stick number, the variations, the bit number, and so on. In your constructions, or would you be able to bound the size of the balls?
Yeah.
I mean, typically you would aim for unit balls or almost unit, like maybe the ratio between the largest and the smallest would be 10 or something. Can you find such a bound? Maybe not. I mean.
Yeah, it's a very good question. We want to search more because, for example, we want to compute the rope length of a knot, which is if we use unit spheres, it's very related with the rope length. But maybe yes, there is something things that we can do. We have our last construction. We can consider the smaller sphere, and we can fill the others with this size. So, for example, in terms of the crossing, we can compare which is the size of the last sphere and the biggest sphere. This gives us a ratio between the size. This is for the algebraic construction. For the first method with the circular algorithm, we have no control about the size of the sphere. We have control about the size of the sphere in the boundary, as in the circular packing methods, but inside the sphere inside, we have control.
Thank you very much.
Thank you. Now I turn to physics director.
I don't have questions. We have discussed lots and lots over the last year, but maybe Kate or want to ask some more questions. I don't know.
We'll come back. We'll
I
make a
will
tour.
come back.
Yeah, I will. Yeah, I will ask them.
Oh, okay. Well, no, I don't have it. Just maybe that it was a pleasure to work with Ivan, and we have a good fun, I think. And I think if you carry with your enthusiasm and your determination, then you will achieve nice things. So, well done.
Yes, maybe we can go back to Professor Stench. Would you have a few other questions?
Yeah, sure. Another question that I had was about, so you've got this ball number bound that you use the cubical orthoplicial packing for. And I'm just wondering, it seems to have convenient properties for this. But is there would you expect that there might be other packings that you could use that would be a little bit more efficient? And is there any point in like trying to do a search through possible packings for alternatives? Or are you confident that it's the best place to do this, to attempt this algorithm?
Well, I think the cubical case with the cubical structure inside is the best place to prove that every link is inside, because we have a square inside what we can use for construct braids, as we proved before. In the other cases, well, there is no square, it's maybe more difficult to construct these braids. But to do optimal construction, maybe it's not a better place. I think we have used, for example, other polytopes, for example, the 24 cell or the 600 cell, to construct other links which are even more optimal. We can obtain more less sphere than 4 times the crossing number. But the problem is that we change the polytop, which normally the structure become much more complex, and we have more elements, and maybe it's more difficult to determine what are the good elements to produce these crossings. But yes, I think that this is a good question that we have to check how to construct optimal construction with other links, or with other polytopes. Sorry.
Another question that I had was, let me look through. Yeah, so all of the things you've considered, all the polytopes that you considered, I think we took something edge describable and then you get a packing, which is a tangency, everything's tangent. What parts of what you've done would generalize to a situation where you've got a packing of, in quotes, packing of circles, but where they're not necessarily tangencies? Because some people have been considering such, almost packings where maybe there's spaces between the circles and stuff.
Well, this packing will be not polytopal, and the problem is that maybe there is no, it not behaves well under duality, because when we have an edge-scribe polytop, we can always consider the polar, which is the dual of this polytop. When it's not edge-scribe, when we do the polar, maybe this dual is not well defined. We cannot apply the Apollonian group in this general case. Maybe there are some special cases that will be interesting. Maybe for we consider, instead of edge-scribe, we can consider ridge-scribe or inscribe, not inscribe, ridge-scribe, for example. And that gives us not a packing, but a packing with the spheres are orthogonal. Maybe we want to construct this kind of construction. In that case, instead of considering edge-scribe polytops, we're going to consider, for example, ridge-scribe.
And do you think there would be a way to have a Descartes theorem in a situation like that?
It's a good question. Yeah, very good question. I don't know. Probably.
All right, thank you.
Thank you. Professor Chen?
So I'm inspired to ask two more questions. So first, you said you computed using circle packing theorem, then in Mathematica.
Yes.
And the computation in Mathematica, how fast is that? So like, what is the typical number of spheres in your picture, in your 3D picture, and how many seconds or minutes does it take?
Well, the secret packing algorithm, I had to write it using Mathematica, but it was my own code. So it was very poorly code. So it takes a lot of time to make a few spheres, so it's not very optimal. But for example, if you want to apply Apollonian packing, producing new spheres, in 2D, this can be done easily. We can obtain very good configurations, but in 3D, after 2-3 operations, it becomes very heavy. So I think maybe with the shader that you used, I think it's more efficient. But we always work with very small examples, so we don't need much spheres.
Okay. Just to have an idea of the efficiency of the algorithm. And then the other question is, it was asked about so to generalize your method to graphs. So I already forget some graph theory, but I remember for non-planar graphs, there is this intersecting number, or what number that is the minimum number of intersections that you have to got when you realize this, when you want to draw this graph in the plane.
I think it's the crossing number also.
Yeah, that's the crossing number. So, but if you have a drawing with the minimum crossing number, so you can regard the crossing as a vertex, and this is a planar graph again, and you can play some very similar trick as you did in your thesis, yeah?
Yeah, that's true.
So it means that there is a hope to get a upper bound for the number of spheres needed to realize this graph bounded by the crossing number.
Yes, I think it's a very good observation.
Thanks.
Yeah, maybe I think it will be probably an upper bound, a linear upper bound for this crossing number, or at least for non-planar graphs.
Yeah. Okay.
I don't know if it will be 5, but linear, I think it's clear that yes.
Yeah, thanks. That would be all my questions.
Sorry?
That would be all my questions.
Yeah, thank you. Thank you very much. Tu aurais d'autres questions?
Thank you.
Tu aurais
No,
d'autres questions?
that's fine.
Ivan, let me ask you just two or three quick questions. Yeah, in your thesis, you have an example of a Diophantine equation where you produce infinitely many solutions. So was this new?
I think so. It was new the geometric construction. I don't know, maybe the parameterization of the form maybe is known.
No, but the point that it had infinitely many solutions.
I didn't say it, but I think so because if there is a parameterization, it will be infinite solution. I think there is a parameterization, but I'm not sure. You mean for the last different equation?
Yeah,
Yes.
I'm not sure it was the last, but it was near the end. Yeah.
That is that every point here corresponds to infinite solution.
Mhm.
So that is true. We don't know if these are all the solutions. So we will put it as a conjecture.
Okay.
Yeah, we think that there is a lot of work to do connecting the equation and this kind of construction.
Yeah, this is what I was going to ask. Do you envision many more applications of this construction to?
Yes. For example, all the card theorem give us a different equation. Integral package will give us solutions for this different equation. We can also, we wanted to apply it also to find Pythagorean triples. We can use this kind of methods. Pythagorean end triples. So, yeah, the question is if you take an arbitrary different equation, maybe how can I find the backing that would be useful to find this solution? This has a work to do there.
It opens a whole new field, maybe. It's very interesting. Regarding your conjectures on the Ball number, yeah, that's very, very interesting. So you prove that for a rational link, the Ball number is bounded above by 4 times the crossing number. Do you think you can extend that to closures of, say, algebraic tangles, for example?
Yeah, for example, for Montesinos games, these are the closure of some kind of rational algebraic link, sorry. I think there is a result about the crossing number that if the fractions are all positive, that the crossing number is always the sum of these are the crossing that we see in this construction. And in that case, we can apply the same, and we can obtain also 4 times. For other algebraic links, the problem is that there is no result about the crossing number. So for rational links, it's very nice because it's just the sum of the coefficients. We obtain the relation directly.
Yeah, but then for algebraic tangles, so even if you don't have a precise, there is no precise result for the crossing number. Maybe you have so you have an expression on the number of crossings you see in your algebraic tangle.
Yeah, you can compare. If you have a diagram with n crossing, then you have 4 times everything.
Ah, that's very interesting.
Yes.
Very nice. Yeah. Okay. And do you think one can devise an algorithm to, given a not even a small one, then to check either that 4 times is the best or?
Yeah, I don't know. That's a very good question. I don't know any method to prove lower bound. I think maybe there's some things to do comparing with the stick number, which is a trivial lower bound. But yeah, we wonder how to prove how to get a lower bound non-trivial, but we don't know. We need a new method to. Someone has to do it.
And a last general question. So you have these applications of Apollonian packings to number theory and to node theory. But in the course of your thesis, which one came first, or did you know in advance that you would have so many applications, or how did it work out?
So I think the history was we first worked with the super packing algorithm. We tried to generalize the 3D, and we were a table. We wonder about this question about, okay, maybe not for collapsing space, but maybe for the simple 3D structure, maybe for knots. We try to do knots with the spheres. We wonder how many spheres we need. So we wanted to construct methods of construct sphere plugins, that we wanted to do some links inside. One day there was this some papers on the orthogonal packing. We found this structure that maybe will be nice for construct packings. With this connection, we found these relations that will come after that. The relation with number theory, the polytopal Descartes theorem, and the connection with the Diophantine equation. So we start with knots, and then it was a big door.
Okay, thank you very much. Let me check again. Professor Stange, would you have other questions?
No, I think I'm good. Thank you.
Thank you. Professor Chen?
No, I have no question.
Thank you. So thank you for all those questions. So now the jury will retire to another room to deliberate, and we will be back. So, thank you.